let's do some optimization. In particular, I'd like to find the minimum and maximum values of some function over some interval. We're going to be following the basic pattern of doing these problems, where we're going to try to find the critical points of the function, and then we're going to compare the values of the critical points and the endpoints and see which ones are the biggest and the smallest. So the first thing I'm going to do is give my function a name so I can refer to it. So that's f of theta. And I want to take a moment to investigate some properties of this function. So sine of theta is continuous. Cosine of theta is continuous. The product of two continuous functions is continuous. Therefore, f is continuous. And then similarly, for differentiability, sine is differentiable. Cosine is differentiable. And the product of two differentiable functions is differentiable. So f of theta is, in fact, differentiable. So we have a differentiable function over some interval right here. And so what the first thing I just determined is that all critical points will be roots of f prime. So critical points are places where either the derivative is 0 or where the derivative doesn't exist for one reason or another. Could be jumps, could be cusps, could be an essential singularity, right? And we just determined by reasoning about the function that it has no such points. So we have the two endpoints of our interval, and we also need to find the critical points, all of which will be roots of f prime. So we need to find f prime. So let's take the derivative. We've got the product of two functions right here. So the product rule. So f prime is equal to sine of theta times minus cosine of, nope, come on brain. The derivative of cosine is negative sine, there we go, plus cosine theta times cosine theta is equal to cosine. I'm going to move the term that's negative to be in the back. It's going to be cosine squared theta minus sine squared theta. So that's f prime. And the critical points are places theta values where this thing vanishes. So I'm not going to write equals 0 there because that's wrong. I am going to go f of c equals 0, f prime of c equals 0 is equal to cosine squared of c minus sine squared of c. And that's a true statement. Well, I'm making it be true because I'm going to find the c such that this is true. So if this is equal to 0, then sine squared has to equal cosine squared. So I'm going to achieve that by going like that because I'm going to run out of space. I'm only doing this because of space constraints. And now I want to, let's see here, take the square root of both sides. But I'm going to be careful, right, because the square root of something squared is always positive. So when I take the square root of both sides here, which I'm going to do, I'm going to take the square root of both sides, I'm going to get absolute values around these two things right here. So cosine squared equals sine squared is the same thing as saying that the absolute value of cosine is the absolute value of sine. So I think the right thing to do is to reason via a picture. So I'm going to draw cosine first. So I'm going to draw some little sketchy sketches. So I'm going to draw cosine over 0 to 2 pi. It looks like that. From 0 or pi over 2. Sorry, pi over 2. At which point it passes through 0, and sine looks like that over this interval. So what luck over this interval, because in particular because we're looking at this here, these absolute values don't have any impact on the value of that critical point. So in general, if we were looking at an interval that was bigger than this, right, then the cosine would dip down to be negative, and we'd have to deal with the absolute values. But only because our interval is from 0 to pi over 2 do we not have to worry about that. So I'm going to go ahead and clear my values like that, only because we're over this particular interval. And if we look at this diagram right here, I think it's pretty clear that value should be at pi over 4. I mean, my diagram is not perfect here because it's, right, it should be exactly in the center. Right, so let's go think about the unit circle. Cosine is 1, cosine is 0, cosine is root 2 over 2, sine is 0, sine is 1, sine is root 2 over 2. So this is where root 2, so it's where these two functions take on value root 2 over 2, and that's going to be precisely true where c is equal to pi over 4. That's a 45 degree angle. That's a 45 degree angle. So, so we have one critical point in this problem, but we also have the boundaries of the thing, the boundaries of the interval 0 and pi over 2, where the function could take on maximum and minimum values. So I'm going to now collect my work. So I have my critical point, and I'm going to collect my work into a table of the values that we're interested in, and then we're going to compare which ones are bigger and which ones are smaller, and we'll be off to the races. Right, if I were writing this on a piece of paper, I would absolutely not have erased that because that stuff is all really important. So we've got some theta values. Those are theta crits. I've got 0 because it's the endpoint. I've got pi over 4 because the derivative vanishes there, and pi over 2 because it's an endpoint. And our function evaluated there, let's see here. So I'm thinking about how much to write down when I do this. So I don't really want to write much down. So if I plug in 0 for theta in these expressions here, sine of 0 is 0, so it doesn't matter what cosine is. Here's f of theta crit. This value is 0. Similarly, if I take pi over 2 and plug it in here, we're going to get, let's see here, well, cosine of pi over 2 is 0, so 0. And then here, if I take this value and plug it in, we're going to have, let's see here, so root 2 over 2 times root 2 over 2 is f. Ooh. So, which one of these is the biggest? Is the half. So this is our max. And this one's a min. And this one's a min. So again, our question was to find the minimum and maximum values of some function over some interval. We found the critical points, which were roots of f prime in this case, because the function is smooth differentiable function over this interval. I found the critical point. This is the only one, pi over 4. I plugged it into the function along with the two endpoints for the function, and we find this. And if you were to plot what the function looks like over this interval, it looks something like that. This is not a perfect diagram of what this function looks like. A half, 0, 0, pi over 2, pi over 4. And we have our maximum and minimum value of our function over the interval. So thanks for watching. I hope you have a lovely day.